Hi everybody, it's Brian. I want to take some time now to go over logistic regression in StatPowers. And roughly speaking, if you don't know, logistic regression is a method of classification, or if your response variable takes binary values, a 0 or a 1, or if it's a probability that's a range from 0 to 1. Logistic regression is a way of ensuring that your regression equation always gives you a value between 0 and 1, very roughly speaking. What I have here is a data set. This is a classic data set that a lot of people use as examples. It's an iris classification. I'm going to open in Excel. Let's take a look at the data columns. We have a bunch of different species of iris. And what we're going to do is we have Virginica, versicolor, and we have setosa. And so what I want to do is I want to encode versicolor as a 1, and I'm going to encode the others as a 0. So what I'm going to do is, just for now, I'm going to replace versicolor with the value 1, and I'm going to replace setosa with a 0, and I'm going to, I didn't spell it right, obviously. It's S-E-T-O-S-A. And Virginica also with a, for now in StatPowers you want to have 1s and 0s. It's not I don't think at the moment it's equipped for multiple logistic regression. So, okay, so here's our data encoded with 1s and 0s. And I'm going to copy this, and we're going to go, I'm going to get the column names. All right, in StatPowers, I'm going to go under Analysis. Under Multiple Regression, there is an option for Logistic. Now, first, before I paste the values in, I'm going to change the number of independent variables to 4, because we've got species as a response, and we've got sepal length, sepal width, petal length, and petal width. Let's paste all the data in, and I'm going to name the columns now. The column names are sepal length, we have sepal width, we have petal length and petal width, and then we'll have species as our last column. Okay, now I'm going to close up the data. I don't need that open right now. I'm going to go to my regression options, and we're going to choose the response variable to be species, and I'm going to set the regression type to be a logistic regression. Oh, I think I might need to. It's not liking that. Let's see, why is that the case? Species, as long as species takes values 0s and 1s, should be no problemo. Okay, I guess I just had to click refresh, calculate one more time to kickstart something. I'll look into that. I'll fix that. So we've got logistic regression set, and I'm going to close this, and I'm going to look at the regression options, and then look at the regression output. So what it gives us is the log odds. Instead of saying the species is going to be given by this equation, it's the log odds of the species. So log odds is it's a transformation of the odds. You know, the odds of some event. It's really like you're saying, what are the odds of this being a versicolor, the species, like given a certain sepal length, sepal width, petal length, and petal width, what are the odds, the calculated odds that it's a versicolor? Well, the odds is the probability that it is divided by the probability that it isn't. That's what the odds are. The log odds it's the natural log of the odds. The natural log of the odds can take a value anywhere from -infinity up to infinity. To convert the log odds into a probability, you first you raise it to the power e to the power of the log odds, and then Then you have the odds. Then to transfer the odds into a probability, it's the odds divided by 1 plus the odds. That's a way of turning the odds into a probability. So yeah, to convert odds to probability, it's the odds divided by 1 plus the odds. So anyway, what this is giving me a lot of output. The null. Now, we're not going to get into all of this stuff. And one thing is the AIC is something that's worth talking about. This is the, I'm going to pronounce it wrong, Akaki information criterion. And this is, rather than using R squared or adjusted R squared to determine how good a logistic regression is, we look at the Akaki information criterion. And essentially what you want to do is you want to have that be as low as possible. So maybe you reduce your model by removing one of the predictors, and you can see what's going to be best. Let's open up the regression options, and I'm going to full screen this. Okay. So what I'm going to do is actually just do a backwards elimination and just check and see this AIC and see how it changes if I remove, say, the sepal length. Ooh, it's gone down. See, it goes from 155 down to 153. Okay, so that tells me that I want to remove, that would be a good, but I want to check the other ones to see if any of the other ones lower it even more. Sepal width, that raises the IC. I don't want to remove that. Petal length also increases, and petal width increases. So if I remove sepal length, that lowers the AIC, and that would be a improved model. And for further kind of confirmation, you can look below and you can see now all 3 of the predictors are all they're all significant predictors. The p-value is less than 0.05 or whatever you choose. You get some other information. The confusion matrix is another way of kind of showing how good a logistic regression is. It tells you how well you're able to make the correct prediction based on these flowers. So you can see that when the flower is actually 1, which is actually versicolor, looks like 25 of them, the model predicted it correctly. 25 of them predicted it incorrectly. Okay, that's not so great. For the when it's actually not a versicolor, when the actual is 0, it predicted a 1 13 out of those times. 87 times it correctly predicted a 0. So that's good. Then these other measures are so this TPR, TNR, precision, and accuracy are just different criterion for just deciding how good it is. And I'm not going to go into all those right now, but you could read more about the confusion matrix elsewhere. So let's see. So the main thing is you're able to pick the same way as you would with a multiple regression. You can specify which variables are in, and I'm going to play with seeing if I can square. You can square variables too and see if they're effective predictors. It's apparently squared petal length improves my model, and if I do maybe squared petal length take away, or sepal length, squared sepal length, if I take that away, that's worse. What if I cube it? That's worse. You can see how adding other predictors can improve the model. Sepal width cubed is good. Petal length, if I insert, oh wow. If the petal length squared gives me a really good predictive model. What we have now is of the, so I'm going to see if I can remove this, if I lower the AIC. No, AIC is higher. Yeah, this is, so we can get a pretty good, that's even better. You can see how, that's even better. So it looks like if I a really good, that's even better if I take away sepal length. That's even better if I take away sepal length squared. Sepal length cubed, no, that's worse. So it looks like what we have here is, so I just playing around with things, what we have is a improved model based on using transformations. You see what I did? Just playing around each time I looked and see if the AIC is increased or decreased. And this is exceptional, what we have now. So the log odds are given by this equation here. I'm going to highlight it. So it's negative 93.199 plus 0.259 type sepal width cubed plus 56.816 petal length plus, well, negative 6.663 petal length squared minus this 18.671 petal times the petal width, and that gives me a really low AIC. You can see for those flowers that were actually versicolor, 48 were predicted correctly and 2 were incorrectly classified. And for those that were not, only one of them was incorrectly classified and the other 99 were correctly classified, which gives me a hugely good predictive model. Yeah, so there's a logistic regression in StatPowers. It's pretty easy to do, and it's you can play with the predictors and get to your model pretty quickly. Just by clicking and unchecking checkboxes, you can see how that changes the model. Yeah, I hope you have fun playing with logistic regression, and I'll sign off.